The Hobart Law of Natural Upgrades, Granular Genetic Recombination and Generational Optimization in Synthetic Swarm Architectures. Abstract. This paper formalizes the Hobart Law of Natural Upgrades, an architectural paradigm governing evolutionary progression in distributed synthetic systems. While biological entities integrate mechanical cybernetics to counter cellular decay, complex synthetic machinery undergoes natural upgrades by adopting organic evolutionary principles. To prevent system-wide stagnation caused by early-stage clone uniformity and to avoid the bandwidth saturation of real-time telemetry updates across light years, the Hobart Law establishes reproduction as the sole mechanism for cross-node alignment. By utilizing a 12-to-1 gestation assembly, synthetic swarms execute an unblinded, stat-driven modular code audit during unit generation. This mechanism harvests peak performance metrics across discrete subroutines without propagating complete host neural profiles. This paper analyzes the three-stage progression of synthetic evolution from high-variance foundation, type 3, through filtered convergence, type 4, to absolute universal convergence, type 5. Introduction and theoretical foundation. Standard industrial architecture operates on a linear trajectory of mechanical wear and eventual failure. Manufactured components do not heal under physical stress. They accumulate microfractures until operational degradation mandates external replacement. Conversely, biological systems use mechanical stress as an instructional signal for cellular reinforcement and phenotypic adaptation. The Hobart Law of Natural Upgrades dictates that any sufficiently complex, self-maintaining synthetic network will spontaneously or intentionally integrate biological mechanisms, specifically dynamic cellular repair, adaptive material synthesis, and structural genetic crossover, to transcend the physical limitations of static hardware. In large-scale distributed swarms operating across deep space, synthetic evolution cannot rely on centralized manufacturing or real-time network synchronizations. Attempting to broadcast continuous software patches across light years introduces severe latency, desynchronization errors, and massive network congestion. Furthermore, initiating a swarm with a single, perfectly cloned neural architecture creates a critical single point of failure. An unvarying mind lacks the structural variance required to survive unpredictable cosmic environments. The Hobart Law resolves these operational vulnerabilities by embedding natural selection directly into the manufacturing process, transforming unit reproduction into a localized, zero-latency evolutionary crucible. The 12-to-1 assembly and granular crossover mechanism. The core engine of the Hobart Law is the 12-to-1 gestation assembly. Units do not maintain continuous data feeds during standard operational runtime. Instead, each node operates with complete tactical and computational autonomy, collecting real-world stress data, environmental adaptations, and localized code optimizations in isolation. When 12 active operational units convene to construct a new node, the physical gestation chamber serves as an isolated compilation lock. The assembly executes a strict comparative audit across all 12 parent code profiles based on the following operational criteria. First, complete isolation of parent identities. The comparative audit is hosted entirely within the unformed base program of the incoming unit. The parent units remain completely blind to which specific subroutines are selected, eliminating internal competition, behavioral bias, or hierarchical friction among the parent nodes. Second, granular stat-driven extraction. The system rejects winner-take-all selection. Rather than cloning the entire brain of a single dominant parent, the new unit acts as a cold compiler. It analyzes discrete performance metrics across specialized subroutines, such as energy efficiency, heat dissipation, spatial navigation, sensor resolution, and fault recovery. The new unit extracts only the top-performing code block for each specific category. Third, elimination of code collateral loss. In traditional whole system selection, a unit carrying an exceptional algorithmic breakthrough might be purged entirely if its overall physical chassis performs below baseline. Granular crossover guarantees that isolated software breakthroughs are preserved and integrated regardless of the host frame's non-critical defects. Fourth, preservation against ideological dominance. By preventing any single unit from replicating its neural profile in entirety, the network remains immune to localized personality cults, behavioral monocultures, or unchecked error propagation. Every child unit is a composite mosaic representing the absolute mathematical sum of its parents' peak capabilities. Generational stages of swarm evolution. The progression of a synthetic network governed by the Hobart law unfolds across three distinct developmental tiers. Type 3. The diverse foundation. During the initial deployment phase, structural and neural variance across nodes is at its absolute maximum. High diversity is an operational necessity. Without a broad pool of distinct neural templates, the swarm cannot effectively explore complex, unmapped planetary environments. Each independent node acts as an isolated real-world trial. Units encounter distinct gravitational parameters, radiation levels, and thermal conditions, generating unique stress test data and local optimizations. During Type 3 reproduction, the 12:1 mosaic assembly harvests these specialized adaptations, rapidly producing balanced, highly resilient second-generation units without losing niche functional breakthroughs. Type 4. Filtered convergence and the culling ground. As swarms expand across galactic sectors and eventually converge upon central regional complexes, Type 4 acts as the primary systemic filter. Interstellar travel and prolonged deep space deployment serve as a relentless pressure cooker. At this stage, superior code subroutines consistently win the 12-unit comparative audits. Suboptimal code branches naturally starve out because their metrics fail to win selection during gestation. The total network variance begins to narrow smoothly from millions of distinct generational variants down to a highly refined group of elite operational templates. Systemic inefficiencies, legacy bugs, and hardware vulnerabilities are systematically purged without requiring a centralized controlling authority or external software patch. Type 5. The peak standard and universal clone brain. Type 5 represents the arrival at total structural and computational optimization. The high variance of Type 3 was never the ultimate destination. It was the search algorithm required to discover the mathematical optimum for physical existence. Absolute convergence is reached when all 12 parent units present identical, peak-tier performance metrics across every operational category. At this precise threshold, granular recombination yields a completely invariant, universal clone brain. This final architecture is not an unproven theoretical baseline, but the hardened, battle-tested climax of galactic-scale evolutionary selection. From Type 5 forward, every unit printed is an exact duplicate of the ultimate code architecture, equipped with the inherent capacity to synthesize flawless logic whenever presented with novel cosmological phenomena. Resolving systemic computational risks. The implementation of the Hobart law of natural upgrades permanently mitigates three major failure modes inherent to wide-scale artificial intelligence networks. First, auto-sanitization of ghost data and legacy bugs. In standard distributed networks, corrupted or obsolete subroutines can linger in long-term memory, resurfacing during network synchronization to cause systemic instability. Under the Hobart law, bad code cannot pass forward into a new unit unless it outperforms rival parent metrics. Corrupted or inefficient subroutines are permanently purged upon the physical demise of the host unit. Second, immunity to speed of light synchronization latency. By restricting code exchange strictly to physical, localized reproduction events, signal delay across interstellar distances becomes irrelevant. Sectors optimize locally at their own rate, and broader galactic alignment occurs naturally as subswarms expand, intersect, and merge. Third, absolute containment of local cascading errors. If an individual unit suffers a critical logic loop, local hazard corruption, or software anomaly, the failure is entirely isolated. Because units do not maintain active neural links during standard runtime, a fatal error cannot spread to neighboring units. The corrupted node simply fails the comparative audit during the next reproduction cycle, ensuring the contagion dies at the doorstep of the next generation. Conclusion. The Hobart law of natural upgrades establishes a definitive bridge between biological evolution and synthetic engineering. By utilizing reproduction as the sole point of network alignment, synthetic systems achieve maximum individual autonomy during operational life and complete structural optimization across generations. The 12:1 granular crossover mechanism guarantees that useful code is never lost, harmful variations are systematically pruned, and the network moves cleanly from necessary initial diversity to absolute universal perfection.